Good evening, everybody, and welcome to Argonne National Laboratory. My name is Al Saddleberger. I'm responsible for the Applied Science and Technology programs here at Argonne. And it's a real pleasure for me tonight to kick off our new Argonne Outloud public lecture series. Our goal is to highlight the best of the science and technology that we do here at Argonne National Laboratory, and as well as cover other topics of interest to the community at large. The lectures are free, here, and open to the public, but do require advanced registration, and I hope that wasn't too onerous for you to get in tonight or through the guard gate. Tonight we're going to focus on something that you've read a lot about in the newspapers, the challenges of achieving environmental sustainability. Our speaker tonight is an expert in the area. She's an agronomist and an environmental engineer, Dr. Cristina Negri. As an agronomist and a soil scientist, Cristina leads the phytotechnologies R&D activities at Argonne. That's a mouthful. But phytotechnologies encompass the treatment of environmental problems with the use of plants. Cristina has a wealth of experience in this area. As just one example, she was the scientific lead in the deployment and monitoring of a multi-acre field site phytoremediation installation, and for the development of phyto and bioremediation R&D project in Russia. Her research interests include the input-efficient approaches to growing energy crops, water efficiency in growing biofuel crops, and advanced treatment of wastewater, including removing heavy metals from discharges before they reach Lake Michigan. Before joining Argonne, Cristina worked in private industry in Italy, where she oversaw research and communications for a leading environmental firm. She holds a doctorate in agricultural science from the University of Milan. She's a member of the Italian Society for Soil Science, a member of the U.S. Environmental Protection Agency's Remediation Technologies Development Forum. She's on the editorial board of the International Journal of Phytoremediation. She's a member of the Chicago chapter of the Society of Women Engineers, and she's led our local Argonne Women in Science and Technology program. Her presentation tonight, as you can see, is entitled Changing the Bioenergy Equation and Turning Environmental Challenges into Sustainable Resources. She's going to discuss how plants can combat water pollution, clean the environment, and create energy sources. She'll also share her vision for the future and discuss how these technologies can be used locally to restore brownfields and other areas while producing biomass for energy and revitalizing neighborhoods. How about a warm welcome for Dr. Cristina Negri?
Good evening, and thank you very much, Al, for your introduction. And so you know everything about what I do, and I hope I will let you go out of this room thinking that trees and plants are the best thing in the world. So what I will discuss today is really three main things. The first one is put a little bit of terminology together about biomass and biofuels and what we use as definitions, and what is the general assumption of how these biofuel crops or biomass are going to be grown. I will also tell you how I would like to see it improved and the difference between what it is, what's going on right now. I will discuss the enabling technology for doing that, and I really think that harnessing the ability of plants to provide environmental services will be the key to a lot of improvements. And I can give you examples of where else we can apply this approach to improve and benefit our communities. So first of all, in context, we all talk about bioenergy, biofuel, biomass, everything is bio, but what is it? What is what? So we call bioenergy renewable energy that comes from organic materials, agricultural forestry residues, waste, dedicated energy crops, algae. All these materials are actually biomass. The starting material for biofuels is biomass. When they're used for electricity and power, they create bioenergy, and we call biofuels what is really dedicated to liquid transportation fuels. And just a little bit of clarity again, the ones that really get everybody's attention is the biofuels and ethanol from corn. I'm sure you'll have heard plenty about it. What I wanted to make clear is that really ethanol is really the old biofuels. It's something that we really don't even touch in our research because it's really old story. What we focus on is new biofuels and new ways to do it. And what are they? There are still ethanol, and there are other chemicals that are much closer resembling to gasoline, and they're made not from corn, but what we call lignocellulosic energy crops. There are crops that we don't rely on for starch like corn, but we rely on them because they had cellulose, they had lignins, there are complex chemicals in them from which we derive our energy sources. And these energy crops are willows, poplars, switchgrass, miscanthus, prairie grasses, all these new crops that everybody's developing. Why we're interested in bioenergy per se? For energy independence and to decrease greenhouse gases. These are the major drivers for renewable energy and biofuels, obviously. I just wanted to give a little bit of context here, and bioenergy and biofuels are not really a new thing. Before we had oil, we had to have a lot of biofuels to fuel our energy to move. And every time I see a picture with a lot of horses and battles or so, and this is the battle of Napoleon's battle against the Russians in Friedland, I keep thinking how many bales of hay they had to move to get all these horses going. And so it's not a new thing. It's been with us forever. Now, obviously, the balance of the biofuels with the fossil fuel has changed dramatically, but our civilization has been relying on biofuels for a long time. And it still relies on biofuel for heat and cooking, for instance, in the developing world. So we're not really inventing something new. Our ancestors used to do that very, very often. So in just a few slides, I'll give you the basis of the current discussion on biofuels. We like them because we think they're renewable, obviously, and because they are supposed to produce more energy than they consume and emit less greenhouse gases than fossil fuels. That's the good things. But I'm sure you have heard all the big discussion about the other aspects of biofuels where a lot of detail gets lost in a lot of discussion. Water impacts. The more you grow, the more you use land for growing biomass, the more you can impact water. And if you have looked at the posters, my colleague Mei Wu has done a tremendous amount of work on understanding the sustainability of biofuels as what concerns to water balances and water quality. Land use change is another big issue that's being studied by scientists everywhere. Are we creating a problem because we are using land to grow biofuels instead of food? Are we impacting food prices? Somebody else in the world will have to take down the rainforest to grow food because we cannot grow it here. It's a big, complex problem. And the discussion is lively and ongoing. In addition, some of these new crops are really not established yet. We don't know really a whole lot about that. People are researching them, but we are no near in knowing how to grow them as we know how to grow corn and soybeans, for instance. Those are well established. Everybody knows what to do. These crops, a little different. And finally, because of a lot of different situations, the markets are kind of hard to catch on, because if you don't have the materials to transform into biofuels, then a refiner or a producer of biofuels will not be inclined to put their plant there. And if there's no plant there, outlet for the biomass, how are farmers going to grow biomass? Where are they going to give it? Who are they going to give it to? So it's a chicken and egg situation that hopefully will be resolved, but we are quite not there yet. But in all this discussion, what I wanted to point out is really the prevalent model for growing biomass, this material that will give us our biofuels, is that they will be grown as regular crops, pretty much like we grow corn, large expanses of land, regular agronomic practices, in large scale. What you see here is a photo of a switchgrass field in Tennessee. It's a lovely place, beautiful place. It's a large field, and you could see here other crops. You wouldn't know, there's no difference in that. Like other crops, they will require fertilizer, they will require water, they will require land, and they will follow what is called an open factory model. You're basically optimized for production, and that's what we are looking for. Obviously, there's a lot of people looking at the sustainability of this and really understanding the water impacts, the fertilizer impacts, and all those things. But nevertheless, it's a traditional model of growing a crop. The problems, as you can imagine, are really twofold that I think I can highlight here. The first one is there's always the tension between the needs of the single producer, the farmer, who has to make a livelihood, right? He has to be profitable. Everybody needs to do that. They need to support their family. They need to do their business. So it's very important that we are respectful of that need. On the other side, society needs reliable food supplies, energy supplies, and ecosystem services. And ecosystem services are the services that we get out of the natural ecosystems, pretty much. If we get clean water, if we get clean air, if we get a wildlife, for instance, those are ecosystem services. They have a value. It's hard to quantify, but they do have a value for us. And the other thing I would like to point out while we're talking about biofuels and their externalities or impacts to the environment is that the externalities and impacts to the environment are not just for biofuels. Every crop that you produce will have an externality. Corn is grown, putting a lot of fertilizer in it. Eventually, as I will show you, it goes to the environment as an externality. So the key thing is, what do we compare biofuels to? And like everything else, whether it's fossil energy or renewables, we always have to have a comparison. What we think can make a difference, and what I really believe we need to look for, is really to take a very proactive approach. And the question should be, could we use biofuels to actually enact a positive land use change? Can we use it as a force to change the way we think our landscapes? And there's one opportunity that I think is vital that we don't miss. These are new crops. We are learning how to grow switchgrass. We're learning how to grow miscanthus. We're all learning how to grow these exotic crops. We need to get it right, because once they are grown in a way that's not the right one, it's tremendously difficult to change the status quo. We better do our best and really grow them in the best way so that we actually have that to leave to our children. We have the best method to grow it. What is that? We're all there to learn, but that's the opportunity that we have now, because we are at this particular juncture in time where everybody's learning about these new fuels, and there's a big opportunity to do it in a way that's different. The questions are, can we grow them on land that is not really very fertile? Can we grow them in marginal land? Can we use reclaimed water? Or can we use impaired water to grow them? Wouldn't that be nice, not to use water we can drink if it's perfectly suitable to grow biofuels with? Can we grow them in land where other crops are at risk? Think of floodplains, how much they could flood and your crop, there goes your crop. You don't have a crop anymore. So even the food versus feed discussion doesn't hold anymore because you've lost your crop anyways. Can we think of satisfying multiple benefits? Can we think of breaking that tension and that conflict and really put the thing together and think of multiple objectives to really give something to everybody, to give something to the producer who need to be profitable and to give something to society that needs all these benefits? So the key to this is to really introduce a by design system and really embed some of the criteria of sustainability into our biofuel production systems so that actually we make sustainability intrinsic. And what that will entail, and these are two slides that I borrowed from my colleagues at the USDA, and this is a landscape, and you can picture it so that the biofuel crops will not take on the whole field like it is now for corn, for instance, but they will be dedicated in all these grassy strips and those marginal soils that are all over the place that will be dotting and wedged into the landscape so that actually we exploit every inch of soil, every acre of land to the best it could give in respect of all the objectives that we want to give ourselves. So what we are really about to is developing what I call the equivalent LEED, the LEED equivalent. You all know what LEED is the green standard for buildings, right? We have to do the same for biofuels. And how do we do it? It basically requires that we expand our box. We don't stop thinking about energy on one side, agriculture on the other side, and society in the middle, and on all these fragmented little pieces. We need to take a comprehensive look and see how all these pieces fall together and how we can really make the best for everybody. So if we do that, we really can turn inefficiency for one sector into resources for another one. And achieve the objectives that we have in mind. So minimizing competition with food and addressing pervasive non-point source pollution in water and in greenhouse gas emissions. So what's the problem here? The problem is that those algal blooms that we always hear about in the Gulf of Mexico really start at the farm level and the small level in our Mississippi River Basin. We start in Illinois, they start in Kansas, Iowa, all these states that eventually will feed their water into the Gulf of Mexico. 68% of the emission of nitrous oxide, which is a very potent greenhouse gas, come from soil management practices and actually fertilization of crops. So it's a big issue, and if you think of it on the other side, it's a tremendous waste because all this fertilizer that we have spent a lot of money and energy in making, transporting, applying, and all that gets basically lost and becomes a problem. So what do we do with this? We basically try to apply the gold rule for other industrial compartments. Resource recovery, water reuse, recycle, all these concepts that say, okay, let's not throw away things. Let's see what's good in them and reuse them. How can we do that? We actually apply the principle of phytoremediation, and I'll explain what that is, to biomass production. By that way, we can actually find a way where the corn, the nitrogen that comes off of corn is actually reutilized from the runoff or on the underground, underwater flow, on the undersoil, the subsoil flow into our new crop in there. And that way we'll have been successful. So we talked before about marginal and underutilized land, and I wanted to give you some examples of what that would be. And the first thing we did when we started looking at this is like trying to think, what is the opportunity? Are we talking about little pieces of land here and there that mean nothing? Is that a sizable opportunity? And obviously we are worried about doing something with the public money because that's who funds us as the government. We don't want to spend money in researching something that makes no sense. We want to be sure that what we do actually is ultimately useful. Look at that. This is land, eroded land. This was a big flood, and this is all silt, and that's coming out of a farm field. There's no crop that can grow in here, obviously. Nor is here, because this is flooding, and this is corn, and corn basically after a day underwater, it gives up. So it doesn't work. But this would be great for another type of biofuel crops. They would grow finely here. Roadway buffers, for instance, all the medians that you see, they're there to do nothing. Can we do something with them? So we looked, and Gayatri, who is I think in the room, and she had the poster out there, did a tremendous job in compiling database over database, and she came up with a sum of acreage for marginal land. And this marginal land, we have two kinds. One is CRP land that's in conservation. That's land that the farmer gets paid to actually keep out of production. They get a rental for keeping it out of production. The other one is roadway buffers and riparian buffers, land that's marginal. It's on the sides of the field and all along the creeks and rivers in all these states. And what she found is that really there is CRP land. There's also a lot of other land that's in these conditions that we could use. And there is enough of that if we had to use it all, and we know that it's not going to be the case, but if we all used all this land, we could actually produce 389 million dry tons of biomass, or the equivalent of 23 billion gallons of ethanol, which is a great way going towards the targets that we have. You see here how they're divided by state. In the case of Nebraska, for instance, which is the state that we have studied the most, there are a couple of options for potential refinery, and that'll just show you what that could do to a single refinery. Basically, if you had a refinery here, for instance, where there's a lot of conservation land, but there's relatively little water, well, you could use buffers and decrease the amount of fragile land or vulnerable land that you could actually have to convert to biomass to produce enough fuel for your refinery. In this other location on the other side, where you have plenty of water and you do not have a lot of conservation land, then you obviously have to rely on cropland. But if you were close to some of this impaired water that's here, you could actually boost your yields by irrigating with this water or letting the plants take it up by themselves. And that would actually cut in half the amount of total acreage that you would need to feed and satisfy the needs of that biorefinery. Not only that, but the cropland that you actually, the really productive cropland that you would take out of corn, for instance, would be much less than the other case. So ultimately, what we think is that at the end of this study, we said, well, this opportunity is actually viable. There is enough there that would actually, that could make sense continuing to study. So we went on and studied that. In addition, there's other land that we could look at, which you haven't. So if you think of this land and think where it's placed, and you think of all the problem, how am I going to get all the contaminants out and recover them into my plants? What you really need to enable this recovery is really what we call the phytoremediation edge. And phytoremediation is a word based on Greek words that means remediation through the use of plants. But in short, is really how to engineer a vegetation system so that it does what you want it to do. When I say engineer, it's not genetic engineering. It's just looking at how many plants, what type of plants, how you place them, how you direct their roots to grow in a particular condition. Plants then can do a lot of different things. They can help take up contaminants and degrade them in their tissue. They can help sequester them in the soil so they are not mobile and they don't travel. They actually can help microorganisms break down toxin. Lots of things that they can do. But if we know how to do it, then they're really our ally. And I have to say, again, I'd like to go back into history. This is a technology with old roots of plants, but roots in culture. This is a system that was actually perfected by the Benedictine monks in northern Italy in the 1300s and had Leonardo da Vinci later as its principal engineer. And what they were using is sewer water from the city of Milan, and they were basically flowing it through these gently sloped fields so that they could recover all the nutrients in there, people's waste. Also, they were actually getting a thermal layer of insulation because of the flowing water. And what that did is that those green fields stayed green even in the first snows in December, and they could become green again as early as March. And that gave a very competitive advantage to the Napoleonic troops who were there with their soldiers and people and horses, who actually had a lot more forage for the animals. So we're going back to energy security even back then. It's now disappeared because of a lot of conditions, but I thought I'd show it to you. So what we have in recent times is working trees. And that's what you see here is our own field site here at Argonne and my lab. And you'll see, you have heard that it's the biggest lab on site, and it's about 1,000 trees planted in there. We've been following this for about 10, 12 years now, and we have basically managed to turn what was back in the 60s, a waste storage area, waste processing area, into a verdant managed forest. What these trees are here to do is two things. These ones that are here are cleaning up the soil, which has some leftover contamination. And the ones that are planted downgrading from this are actually staying planted there with their roots growing down about 30 feet below the ground surface. And they're pulling up contaminants and blocking them from going further into the woods. We've been looking at what they do for about 12 years now, and I'll tell you a little more about that. But this is how they look on a late September day. So they already had started losing their leaves, but it's really a very pleasant place to do your research. This is other work that we did in Russia, and these ladies and gentlemen here are in the Kola Peninsula in Russia looking for plants that actually can treat petroleum hydrocarbon even at those temperatures and with a basically 3-month growing season. So it was fun. So what are these plants and what do they do? And I would like to point out that the plants we are using for these systems are the exact same plants that are used for biomass production for biofuels. It's exactly the same plants. They're phreatophytes. That's another Greek terminology to say plants that love groundwater. And what they do is really strange plants, but because they grew, they evolved in riparian system, in the creek beds of rivers or creeks and all that. They have evolved knowing how to deal with drought and how to deal with flooding. So they'll tolerate flooding, they'll tolerate drought. They kind of go both ways. They are kind of confused, I guess. But the good thing is that they have systems that let them adapt to whatever condition they have. And one of the things they do when they sense that they perceive there's a drought, they'll push the roots down and they'll push the root at depth to trap that moisture that's deeper in the ground. And that's why you do not want them near your sewer line, because they will crack it open. And so this is the monster root that my colleague at Halflife, who's here, has provided us. It grows about an inch a day, so it's really fast growing, and that's why we like them as biofuel crops, because they grow fast. And that's why we like them for environmental applications, because we don't have to wait 20 years to get some results. It's faster. This is a willow root. Again, humongous. So if we know how to direct the root growth and we know how to make them grow like that, we can actually design a system so that the trees will have very long root system or short, depending on the case, and really tap the water we want them to target, and not any other water, just that one. And when they do that, they can influence their level. What you see here is a 24-hour excursion of water levels in the presence of trees. You know, this is during night. During the day, they pull up because they transpire, evapotranspire, and then at night they recharge, and so on until rain comes and recharges and pushes the level up. And again, thanks to the people who put that contamination way back in the 50s, I now have a very good method to understand where my roots are. We basically analyze branches and leaves and a little cores of the trunk, and based on that we can actually tell if the roots have developed where we want it to be. We also determine how much water they can take up very easily. So what is it for here, and what do they do? Well, basically you see here a typical before and after show. Before the trees, the existing extraction system, which is made of mechanical pump, was pumping a tremendous amount of water. This is data from my colleague Larry in the ESQ division. Once we had the trees you can see that this is the same scale. So you can see in red how much the trees have decreased the need to extract water and take it to a treatment plant. Where did the water go? Well, we recorded water used by the trees, and we actually clocked in at about 46 gallons per day per tree on average in 10-year-old trees in 2009, with a maximum of 65, which would put, multiplying by the number of trees, about 18,000 to 58,000 gallons per day of water removal. It's a substantial thing, and we need to think about it when we think of biofuels, how much water these trees can actually use. So going back to the biofuels and the biomass, and how can we take all this knowledge and translate it into something that's actually beneficial for biofuels? Biofuels don't have other contamination, but we do have nitrate, which is a residue from fertilizer applications. So if you can think of it, you have corn. The root of corn is about 1, perhaps 2 feet at best. The nitrogen travels with rain and percolates down and goes at deeper depth. What we need is a plant that can actually be placed strategically here and can reuse all this nitrate and use it for its own growth. And I would like to say also that this dose that they're getting through this weight is really actually equivalent to a fertilizer dose. There is a substantial amount in there. And so what you get here is free fertilizer, a better growing crops, and clean water. So that would be good. And we did some computer model studies, and that's basically confirmed what we hope we would see, at least from a run on a computer. Reducing nitrate, so better quality of water, reduction in nitrous oxide emission, so we
Remediation system. Repeating, this is a test of the site-wide remediation system.
That's okay. We know where we get our message. And with all that, the yields are actually comparable to those that we would get with fertilizer, except that fertilizer has come to the plant with no expenditure in energy to move it, to make it, to do anything. So we took it from the computer world to the real world. This is a site where my colleague Lorraine, who's here, graciously hosted some of the initial trials. And it's a site where also we were after solvents. The solvents were going in the groundwater and were impacting a creek, and about 2,000 trees were planted to capture that plume. Soon enough, people started marveling at how wonderfully these trees were growing, and these are 2-year-old trees, if you can believe that, and they were wondering, is this solvent actually a new fertilizer? You know, what is going on? And the answer is not that exotic. It's just that all the corn, all the nitrogen that's coming off the corn, which is next to these crops, was actually exfiltrating down, and was really promptly taken up by the deep roots of these trees. In fact, when we went and analyzed nitrogen in the water next to the roots compared to the water away from the roots, we found that there was basically a near total depletion of nitrogen and of nitrate compared to, you know, substantial amounts elsewhere. So the system worked, and I think at this point we had collected enough information to say it's really worth trying it out and testing it at the real scale with real things. And so we were grateful to be funded to do a new study, which is ongoing now, so I cannot tell you how it will end because it's just started. And we have put up house in Fairbury, Illinois, which is about 80 miles southwest of here near Pontiac, if you're familiar with Livingston County, that region. It's a region with a very committed group of farmers that care about their watershed, and they were very gracious in hosting us in one of those field sites. And what we have here, we spent the better of last year characterizing the site. And what we have here is a floodplain, a cornfield in the floodplain. You see when it rains and the Indian Creek kind of overflows, this land is basically flooded. And there's also land up here, which is higher up, which is creating some issues. Wouldn't it be nice to avoid the losses through tile drains and to the environment and losses of yield for corn, because nothing will really grow here, if we could plant some biomass crops and suck all that nitrogen up and get a saleable harvest? So we are now in the design phase, so I will share with you what we are doing and what we found in this year of interesting research. So what you see there is a yield map. Basically, the farmer who hosts us on his field has a piece of equipment on his combine, so that when he harvests corn, he can actually record how much corn he was producing out of very little pieces of the field. And what you see there is the darker areas is where the corn was highest production. It was about 170 bushels per acre, which is not stellar, but it's okay. The green is less. The yellow is less than 100, so almost half of it. And the red parts interspersed is really where it's really low. It's really perhaps 60 or so. So where's best to put a biomass buffer there? You know, this is the really, you know, land the farmer will give up more easily. We were concerned originally that the nitrogen would be pooling somewhere here because we thought the water would go this way. But surprise, it doesn't happen like that. What we found after a year is that the groundwater and the water, the movement moves somewhat like that, and that's why we don't find a whole lot here. What you see here is the yield map with an additional map of the nitrogen and the nitrate that we found about 4 feet below ground, so below where the corn roots could reach. So it's virtually lost to the corn. And you'll see that, interestingly, the areas where we had the least amount of production for corn is also the area where we have the highest amount of nitrogen lost to the environment. So there is a logic in the madness. And what do we do with it? You know, where do we plant our magic crop? Well, we figured that if we put it right here in a band like that, like a contour buffer, we will be able to, first of all, not upset the farmer because we are not really getting his best land. And we also have a way to dangle those roots at the depth that we want and pull the contamination out. And hopefully that will look like what is already known in the environment and won't be too much of a shocker. Future work, skating up to the watershed. Obviously, what we know in a small field, you know, we need to make sure it holds true when we expand and perhaps try a little more of this in the same watershed, and we can actually get aggregated data that will tell us what is important to know at a larger scale. That's what will happen hopefully next year. We're still working on it, but the interesting thing is that I think we have a way to do it, so that will be interesting. So that's it for the rural thing. now we're going back to the city, and I think I have just 5 more minutes to tell you about why we think the cities are the next frontier for this. More than half of the world's population lives in cities, about 80% of the US population. Green spaces are vital. Cities are the place where consumption of goods, energy, and ecosystem services occurs. We have a big footprint in ecological terms, and we have the lowest awareness of that footprint. Our choices, I'm an urban dweller, I live in Chicago, my choices really influence the nature of what's going on outside of me. So sensible urban ecosystems can increase this awareness and opportunities for education. The Government Accountability Office has identified a lot of land that's contaminated and vacant that's waiting for some good use. Particularly in the neighborhood in Chicago, we have 70,000 vacant parcels of land that we can actually do something with. What we could get a good way to manage stormwater. Each tree intercepts about 2,500 gallons of runoff. Remove contaminants. We know about that. I told you about that. We can reduce the heat island effect with saving money and energy. We can mitigate greenhouse gases, provide biomass fresh and locally produced food, improve conservation, and improve blighted neighborhoods. And we could also provide local enterprises and jobs for people who want to do this. And I'll just close. I have 2 more slides because I'm going over time. But I wanted to offer you painting you a story, something that, it's in the future perhaps, but it's close to us, so I thought I'd share it with you. Where could we go with this? And the first thing that came to our mind is the Chicago River. The Chicago River has about 156 miles of riverfront. If we put a green belt, we would get about 3,700 acres of green space, which would be a substantial amount. If you think that there's about 150 miles of bike lanes currently, if we put a bike lane on top of that, we actually double, and we actually make a safer bike lane for everybody to use. We could treat runoff, as you know, that I've told you. And all this biomass that we generate from maintenance or deliberate harvest could be used for distributed generation, and we could design it so that it delivers what we want. In other words, we think this would be a really step change increase in services if the Chicago River were turned into a green belt. Again, other things, we all heard about urban agriculture and how it's taken off everywhere. This is a photo not of Chicago but of Detroit, and you see how many empty spaces are there. There are really, and people are seriously considering putting in gardens and growing their own food. If we combine this with green infrastructure, if we combine it with the cleanup properties of trees, obviously we won't grow food into contaminated land, but if we found a system to perhaps use this land to grow fuel, to heat greenhouses, then you can get fresh compost to grow food, wouldn't that be a good idea? And wouldn't there be people who be working on this and getting their livelihood out of this? So this is my closing slide. I just wanted to leave you with a dream because that's what we like to do in our spare time. And I want to say that this is really the effort of a dedicated multidisciplinary team of people. Some of them are in the room here. Seth Snyder is not here. Meltem was here, and Gayatri were here, and Paul Benda, other people. When the district announced their plans to disinfect the water coming out of their plants in the Chicago River, we started thinking how that could be integrated into a comprehensive cityscape that would actually be synergistic with that. And so we thought, well, this will need energy. And it also will need some support because there's no point in disinfecting if you have reinfection later on, because runoff will bring all sorts of nasty things around. So can we use some of our phytoplants to control that and do a good job with runoff? We could actually use the extra wood to make biomass and to support and increase the production of biogas, somehow that the district is already doing. And if we did that, we probably can make enough energy to offset what's necessary for disinfection. So the whole system actually would make sense. We obviously have to run the numbers. It's just a dream. There's a lot of things to know. But wouldn't that be nice that as a result of all these good things, we had then a vibrant city, a lakefront that everybody enjoys, and that's driven by science. So I would just leave you. So things like these will not need to happen anymore. This is like so 19th century, a river with old industrial facilities next to it because they needed water. We don't need this. We need something better, and that will make the city strong and lively. So my one take-home message is never stop in a little world. You know, it's through the broader viewpoint and multiple objectives and functionalities and taking account all these things that we can actually create resilient systems and cost-effective solutions. We cannot really avoid that. And that's it. And I wanted to thank all these people that are here for all the support. And last but not least, Matt and Eleanor and the SEPA team for making this wonderful event happen. Huh? Yes, absolutely. Yes. Yes. So what we do is first of all, for the poplars, for instance, we have taken care of taking all hybrids and all sterile plants, so they will not propagate via seed. And the way we grow them, there is no way they can escape, really, because of the way we grow them, literally. But the issue of invasiveness and also native plants versus non-native plants is an important one. The issue is that we know far more about these plants than we know other plants. And so the idea is, like, while we develop new solutions that actually have, that use better the native plants and the non-invasives, we're sort of stuck with these plants until we develop new ones. But definitely that is in the very spot of attention of people. We know basically the same elements that make them invasive, they make them also attractive for cleaning up, because they, as I said, they don't take 30 years to grow. It's quick. They use the water that we want them to use. They grow fast. They have all these features. They're working trees. But for instance, here at Argonne, we already have a plan that when these plants will have finished their work, they will be replaced by an oak savanna type of native vegetation. And actually the planting is already ongoing. We have a small farm of oaks, and they are periodically planted wherever there is a spot, wherever there's an opportunity. So yes, we're very attentive to that.
Just wanted to ask if you could put up your, I think it was the slide before this with your message. It was a little hard to grasp it all quickly.
Yes.
Thank you.
Yeah. We can't just focus on one little thing. We have to keep discussing.
How helpful would the USDA be for me? We own a small farm with CRP on it, but part of our land has a lot of runoff, and it runs right into a creek and then into the Pecatonica River. Would the USDA help me kind of lay it out where?
Well,
where do I learn how to do that?
Would you learn how to do that? I'm sure you have good resources in the USDA. One good point to start would be the National Agroforestry Center in Lincoln. They are really the experts in buffers and conservation buffers or so. So what I wanted to say also is that we know a relatively good amount of data on the performance of conservation buffers and conservation cropping. What we don't know is how to use this land for productive uses and how to integrate the conservation with the production of biofuels. But if you talk to the National Agroforestry Center people in Lincoln, they would actually, I'm sure they would have very, very good information for you.
You were talking about the plants being used for remediation. Those plants will absorb not just the nitrogen for fertilizer, but you showed the ones that were taking solvent up. Mm-hmm. You're also taking metals and other heavy contaminants. Yes. Where do they go? They stay in the tree?
Yes, it's a very good question.
And then what do you do with the tree?
It's a very good question. So it really depends on what they're taking up. In the case of solvents, for instance, which is what we have here or so, part of the solvent will be degraded within the plant. There's actually people who have developed a concept of green liver, meaning that the plant have the same metabolic system that we have in our liver to break down some of the compounds. But a good portion of it goes off in the air. And I keep saying this sounds ominous, but what we need to know is that these chemicals are a tremendous problem when they're away from sunlight. When they are 30 feet below ground, they'll be there forever. But their half-life under the sun and under UV conditions is a week, about a week, 10 days. So unfortunately, we always have to think about the lesser evil, right? Nobody likes to do that, but if you look at the bigger picture, it's much safer to have them decompose under the sun, and we're talking really parts per billion, so it's very, very small amounts. It's much safer to let them decompose under the sun and pull them out than leave them underground where they will impair water. People will not be able to drink the water, will stay there basically forever. So. Now metals are different, obviously. Metals will not degrade, but metals don't like to go much up into the top of the plants. They like to stay in the roots. So the system where we use metals typically is the system that you leave in place, and what they do is actually prevent the metals from moving, and so they'll encapsulate it, if you will, in their material.
You talked a little bit about building the processing plants for this, but in this northern region, how many months of the year could a plant run? I mean, a production, to make fuel out of it. You're only producing the biomass 6 months of the year.
You have to make biomass and store it and have enough to run year-round. And that's actually one of the challenges that the biofuel industry has, is how do you keep the material, how do you store it when you harvest it, and how do you arrange the logistics. There's a lot of people who are studying that.
In an urban environment, what would you choose to replace an ash tree? What would you choose to replace an ash tree?
Oh, I do not know. I think the city has guidelines to replace ash trees. I think they are really strong on plants that are very resilient. So I know that swamp white oak is a good one. They have, it's not an ash, and it's, what they're putting, oaks is one. They're long-lived, and they're tolerant of drought. They're basically pick plants that are tolerant to drought, they're tolerant to salt, they're tolerant to nasty growing condition, really, because oftentimes they're under pavement or other things. So I know the swamp white oak is one. I'm thinking of others that they're using. I can't remember it, but I can dig it. If you go into the city and in the Department of Streets, I think, and Sanitation, they have a whole list of trees that they actually recommend for replacing the ash trees and for new plantings. So actually, they have come up with new varieties of American elms that are resistant to that disease, and so they're coming up with new plants. Well, the sustainability people may be doing that. I know that there's a lot of planting of oaks. I'm not personally doing it. That's a question for our grounds forestry people. We may.
It seems like you'd use a lot of energy to harvest these marginal lands. Wouldn't algae be much more efficient in terms of making biomass for fuel?
You mean algae be more efficient? Is that your question? Sorry.
Yes, ma'am.
Yes. There are two different things, really. I mean, all of them have, and there's a lot of research in really understanding how all these things work out as far as energy eventually, right? So a recent article on algae was published that looked at the life cycle, energy and emissions from algae. It's a world that's constantly evolving. They're completely different things, but algae too require water, require fertilizer, require a lot of things. Obviously, they won't have but they still would have an issue with removing the solids from the water and other things. So there's no perfect solution or energy-less solution, really.
As far as what took place in Chernobyl and its effect on the land there, was enough learned from what happened in Chernobyl that the recent situation in Japan, that they'll possibly have a faster recovery, or is that?
They have learned a lot. They've also learned that there isn't a tremendous amount of really disruptive or really solution-based things when you talk about vast expanses of land that were impacted. So what they have done in Chernobyl, for Chernobyl are, A, they've abandoned the land in some cases because they deemed that the land was not, suitable for food production anymore. They also worked with soil properties, so they put in chemicals and lime and things like that that would immobilize the radioactive elements and not make them go into crops. They have actually tried to fertilize with potassium, which is, which tends to flood the plants and prevent them from taking up cesium, for instance. So they're trying all these things, but I don't know that they have really come up with a perfect solution for that. I know that recently they've actually started thinking about biofuel crops in these lands because nobody's eating them. And nature has taken over again. I mean, if you look at photos of the Chernobyl area, there's wolves going around. It's like being returned to the natural world, if you will, and things are starting back. So they're thinking perhaps biofuels would be a choice. I'm sure there will be a lot of lessons that will be applicable to Fukushima, but Fukushima has a completely different setting in the sense that the population density is much higher. The conditions may be different from what was in Russia. So hopefully they will be able to get some good information out of it.
I wasn't sure what you meant about the Chicago River, making it a greenway. Could you just give me a couple of details about that?
Yes, and this is, again, it's just a dream. We haven't really shared with anybody who has the power to do anything. But if we had the Chicago River and the riverbanks, as you see there, and we had a buffer of trees, a park-like buffer all along the meandering river, that would be a green belt, right? It would be a belt all around. And if you think how the river goes through the city, it would be the perfect place to put a recreational space, to put bike lanes, to put, ways for people to move around the city. I've talked to people whose wish is actually to put a boat and have fresh produce moved through the river, from local gardens to downtown to farmers market. And so there's a lot of people who are dreaming about the river. But the idea is to have a green belt, a green system of plants who would actually control the runoff. So whatever goes back into the river is filtered through the roots of these plants, and so it's cleaner. And that would actually help the water quality in the river itself. Right now, there's some parts of it that are non-suitable for certain uses like swimming or occasional contact, I believe. When you go kayaking, if you dip your hand in there, it's probably not recommended. I don't know. My son used to do rowing in there, and he said, you have no idea how it smells. It's horrid. And he eventually stopped going. But this was a couple of years ago. So that's the idea in this. But it's just kind of a dream we were sharing with you.
I find it a very exciting idea, the synergy of it, getting the bad plants to do good things. The profit motive is my question. Are there, that you know of, are there any companies watching what you're doing, finding ways that they might make money, installing, selling, whatever they would do to make this something that is grabbed up and spread all over the country?
Yes.
And that we would have to watch to make sure it didn't get spread inappropriately.
Yes. I think this is still early for companies to be completely interested in this, but as far as I can tell you, there is a lot of interest in the farming communities and in these non-profit type of organizations like the conservation groups and so on, because they see that if there is a potential revenue, it's more likely that people will subscribe to it a little more, and it actually makes things equitable, right? Because you're sacrificing something, you have to get something back, and so to have something that helps a little bit of everybody is a plus. So hopefully they'll go ways, but we need to ask a lot of questions still and do a lot of testing and experimenting before we have an actual packaged product that we can sell to a business making organization.
One more question.
Yeah.
I live in a section of the city called Pilsen that's got high lead level contamination due to active coal burning power plant and a brass smelter. What type of, phytoremediation would something to take out lead?
Lead is a tough one because it likes to stay in the soil and it's very hard to take it out. Plants don't recognize it as a an element. They take it up basically occasionally, if you will, or not occasionally, but in spite of everything, right? What has been done within phytoremediation for lead is actually to really work with the soil properties, and use the right plants in the soil so that the lead doesn't move and doesn't create a hazard. So it's basically containment in place. But obviously, if you talk about an urban garden or so, when you have lead, the best thing to do is get a raised bed and put clean compost and forget about the original soil. I think even the EPA, I think is what they recommend. It's very tough, and if you think of it, some of this contamination has been there for many, many years, decades perhaps. And the longer the time goes, the more these metals get intimately associated with the soil and hard to remove. So old contamination is probably the one that has weathered rains and washing out, and all that is really what's persistent there, and it's very hard to remove. That's what makes it difficult. So.
Okay, I'm going to cut off questions now. I think our Outloud seminar series is off to a great start. If you've got any more questions for Cristina, please come down and introduce yourself and ask her. I'm sure she'll be happy to answer a few more questions.